This section will be answering part 2 of our Viva, which will be proving that if we have a ring homomorphism from R to S, then the kernel of this ring homomorphism is an ideal of R. So first, defining R and S as our rings. Fairly obvious, since they are rings, they follow these axioms, which are shown here. And by comparing theorem 4.1 and 2.2 in our books, we find that any ideal of R is a subring of R. This means that if we can show that the kernel of the ring homomorphism is a subring of R, then that would imply that the kernel is an ideal of R also. So, this section will be trying to show that the kernel is a subring of R, which therefore will mean it's an ideal of R. So for this to be true, the kernel of the ring homomorphism must follow these axioms. We find this from the book. So for all AB element of the kernel of the ring homomorphism, then the additively or subtractively these elements will still be contained in the kernel of the ring homomorphism. For all AB an element of the kernel of the ring homomorphism, then the A times B, so timesing the elements, will still contain, will be contained in the kernel of the ring homomorphism, and that the kernel must be non-empty. If all these axioms hold, then that would mean the kernel of the ring homomorphism is a subring, which then would show that it's an ideal through comparing theorem 4.1 and 2.2 from our books. So we know that ring homomorphism under addition is a group homomorphism. We know this from the definition of rings and homomorphisms, which pretty much satisfies the first axiom. And we can say that from the definition of the kernel, that the kernel is a subgroup of R. We know that from the definition of the kernel anyway. And now if we were to try timesing them within the ring homomorphism, we know we can write this as you know, it's just so if you were to expand it, this would swap over to that. Pretty fairly obvious. And then as A and B are both elements of the kernel, we can call them 0s because the elements contained in the kernel are the identity elements. So therefore, identity times by an identity also just gives us the identity. So through this, we have shown all three axioms are satisfied from the kernel of the ring homomorphism. Therefore, it is a subring because all are satisfied. And as a result, as the kernel is a subring, kernel must also be an ideal of R by comparing theorems 4.1 and 2.2. Thank you.